Our third challenge speaker is from Hewlett Packard Enterprise. Hewlett Packard Enterprise. Jon Buckingham, who's an R&D engineer. Jon has been designing ASICs for about 20 years, from tape drive formatting through compression, encryption, and now working on PCIe-based accelerators on HPE store-served products. He's been interested in formal verification since DAC 99 and has been increasingly using properties and formal proofs as part of the design process.
Thank you. So I'll come and stand over in the middle so people don't feel so left out over this side. I'm in quite a small ASIC team of about a dozen people in a vast sea of software engineers elsewhere in our division. So we kind of feel special in our little group, but we get to do quite a diverse range of stuff, everything from requirements for the product with product level involvement through the spec for the ASIC, the actual implementation of the ASIC, obviously, verification, which is why we're all here, and then turn on. So we have reasonably broad view. It's kind of like being a small company, a startup within a large company in a way. So our challenges, as we view them, I'm also predominantly a design engineer, and being a small team, we break all the rules and quite often do verification as well as design, and sometimes even, shock horror, verify our own designs, because that's the way the world works sometimes. But, okay, so our challenges as we see them at the moment in our little business is coverage from FPGA prototypes. So we'll talk about that. How can we be sure we're getting good value from our FPGA work? Real system use verification. So are we really verifying it as it is really used in the system? Are we really finding the sorts of defects that real end users will be finding? And then the final one is a bit trite, a blindingly obvious one. The whole point of all of this is to catch all the showstoppers. We do not want to respin that chip. So we'll just go over that again and what a big deal that is, because it sometimes can be easily forgotten. Okay, so the first one, FPGA prototypes. So think about the situation. They're expensive. Costs a lot of engineering time to put an FPGA prototype system together. We've got PCA maybe involved as well, maybe special software, and obviously the part costs. We typically use them for accelerating software turn-on. I think we've heard about that from the other speakers already. And we also really like to use them to try and find any ASIC defects early. Anticipated extra verification we'll get from this is because of the final bullet, really. We can do so much more with faster run times. The clock tick period is a lot quicker on FPGA than a simulation, so hopefully we can catch issues with large counter rollovers, and hopefully the system level scenarios, which is our other issue, hopefully we can address some of those more easily because we can do so much more stuff. The challenge is to find the defects. So if we concentrate on what I said, as well as turning on software from an ASIC perspective, particularly from a designer, we want to find those defects. So does the software used really emulate real system use? Is it production code or special test code that's running this FPGA system? How representative is it? How can we measure the coverage we're getting? Okay, so we're doing lots of stuff. It's not as obvious how to measure coverage sometimes. Are these large test runs actually doing anything new each time? Wouldn't it be cool if you could somehow in the FPGA process synthesize the coverage you've got written in your properties, including assertion preconditions, and get some sort of data out? And the third primary bullet there, can we find defects in time, i.e. before we do any form of netlist release? So we need the FPGA prototype. The big challenge there is getting it working early enough to be beneficial in finding defects. And then there's compromises, performance. One of the reasons for maybe doing an FPGA prototype is to interact with existing system components. Performance is clearly going to be an issue there. Different IP. If you've in your ASIC, there might be using a particular vendor's interface IP perhaps, and it might be different in your FPGA. So you need to make sure that you don't waste time verifying the FPGA IP if that's different from the ASIC IP, from the target ASIC IP. And be very careful if you're having to change your RTL to be able to synthesize it into FPGA. It might synthesize no problem into standard cell technology, but going into FPGA may be very different. We really try very hard to have identical RTL, so we'll try and synthesize for both. And debug isn't that straightforward either. If you do find issues within your FPGAs, even though there's lots of probing options in there, it's not straightforward, and sometimes that changes the design, the defect goes away, or it's harder to track. So getting return on investment is challenging with an FPGA, but usually useful. So real system use verification, this is another one we worry about a lot in our little group. So let's just talk about this. So constrained random is hard. We've certainly heard about that from the other guys. So that kind of that's another reason for having separate verification teams, because the methodologies and languages are complex, so they're hard to pick up. Test benches for random with good coverage is a very challenging design problem in itself. And error scenarios are the hardest. We often find generating errors randomly with and aborting and restarting, getting all your scoreboards to pick up and start again after you've had an error and some sort of abort. That's the really critical stuff in terms of real system use. Does it work after your error? Do all your scoreboards clean up and restart properly? Do we know the system architecture well enough, particularly in the verification team? Are the documentation methods good enough? Documentation is something most people hate, and it's often ambiguous, too wordy, unreadable. It's well worth putting some effort into having really good, terse, concise documentation. And can you write system-wide properties? Are the current tools up to that? Are PSL or system Verilog assertions practical for doing big system-wide properties? How can you prove you've had particular errors, brought down the system, brought it up again, and done transfers again afterwards? That's a hell of a property to write. And so whilst doing all of the above, the verification team has really got its work cut out, and does it fully understand the system as well? And what about asynchronous interactions between two particular ASICs, perhaps, bringing them up? If you've got aborts and so on, do they... there's always a danger with verification to fall into some sort of godlike mode where you can see both devices that in practice are completely blinkered from each other. Can deadlocks occur? These are all real problems. So catching all the showstoppers very quickly then, system level defects. We need to, as I mentioned before, we need system fully, are the specs correct? This really, random helps massively, but only if really well designed. RTL languages, I thought I'd throw this in, having come from, worked in both VHDL and System Verilog. We do struggle sometimes with the loose definitions of some of these languages. Do the EDA tools consistently interpret these languages? I'm not convinced they necessarily always do. Other tools, obviously gate level simulations, how much should we do, linting, everyone does that. Are our rules good enough? And what about all those synthesis warnings? That's all part of the verification challenge. And very quickly then, as been mentioned by both the other guys, people and teams, really, really big problem. System knowledge isn't just about tools, it's about how much people understand the business and the product they're actually producing. That's so easily forgotten. Second bullet, I personally think is really important and easily forgotten. You've got to design quality, and you can't rely on testing it in. So give your designers plenty of time and give them the tools as well. And if you can, keep those designers and verification teams together, because if they can talk, they'll really do so much better. And as a designer, e-sequence writing really isn't that hard if you get your head around the language or System Verilog UVM. Okay, I'll better stop there. Thank you very much.
Thanks, Jon. Are there any questions for Jon? Yeah, okay. I just nearly walked into that.
That was right.
Yeah.
You mentioned that the FPGA testing you're using it to accelerate software development. Also mentioned using it to indicate bug stuff. Are you running any stimulus to make bugs, or is it
well, that is the challenge to Oh, I'm sorry. The question was, what stimulus are we running on the FPGA prototypes in order to catch defects in the ASICs? So that is the challenge, and because it's early in the program, we end up having special software infrastructure written, which is kind of why I highlighted that, because that's yet another set of software which we have to try and make sure is reflective of the system. So yeah, we're writing separate verification code in effect to run on that FPGA prototype. So that's a whole new class of testing that's being done, and as I think Andy mentioned, that it's yet another addition on the stack of stuff that gets done.
I am Doug. You seem to do a lot on the shoulders of your FPGA prototype. Do you do emulation at all?
We haven't. Sorry. Do we do? Yeah. The question was, do we do emulation before FPGA prototypes? In our team, we haven't. We just haven't had the time to explore that. It does look interesting. The issue we usually have is we like the prototype to fit in a real system if we can. So there's some issues there in terms of connecting it into the real system. Maybe solved. Maybe it's one more thing we need to investigate. Yeah. Sure, we haven't done that. Not because we've evaluated, just there's only so much we had time to investigate so far.
Okay.